a set of nodes in input graph as a node, or create a set of different clusters of nodes. If you recall, in down sampling approaches, once we select the nodes, we discard the importance of other nodes. We do not uh, try to take information of unselected nodes while creating any other information associated with coercion graph. Here, we are trying to generate supernodes without losing any information, and the supernodes are generated using the clusters, which are set of nodes. Again, similar to downstreaming based hierarchical graph pooling, there are three key elements in a supernode based graph pooling. Generate the supernodes for nodes of the coercion graph, generate the graph structure for the coercion graph, and generate the node features based on the coercion structure. For example, let's take an example of 5 nodes. And let's say we generated a cluster here. Then we can, using this cluster, we can generate, let's say, 1 dash, 2 dash, and 3, 4 dash. So we have now new graph structure, 1 dash, 2 dash, 4 dash. Here remember that I have not unselected 1 or 3, but I have clustered them together to create a new node 1 dash. Similarly, 2 and 5 are not removed. They have been clustered together to create 2 dash, and similarly 4 remain the 4 dash. So that is what is done in a supernode based graph pooling. And after that, we are going to use this coerced graph structure to generate node features based on the graph structure. There are two methods. One is diff pool, another one is eigen pooling. The diff pool use a differential approaches to generate a supernodes from a given graph structures, while eigen pooling use spectral clustering based approach to generate the supernode. Let's look at the diff pooling or diff pool approach for generating supernodes. In diff pool algorithm, we try to learn soft assignment metrics using graph convolution neural network filter. Here, the assignment matrix is then used to map the nodes in the input graph to supernodes in a coercion graph. So let's look at the assignment matrix generation. Here S denotes assignment matrix, which is of dimension R in cross N out. Hence, you can see that the columns of S indicates new super nodes, where R rows indicates the input nodes. Then softmax is applied on the output of GCN, which takes A in and F in as its input. If you recall, we have a set of filters in GCN and then there is a pooling layer. In several cases, we have the output of the last filter in a particular block. If you recall the block, idea of block, where we have several blocks and each has a layer of pooling, then again it goes to the set of filters, then pooling, set of filters and pooling, correct? So this is a block consists of these three operations, block 1, 2, 3. So we can use several GCN filters in each, it can be stacked here. So here the input can be from pooling layer or also from the last pooling layer or also from the filter layer possible. So there are certain approaches where the inputs of the pooling layer is used as the output of the previous pooling layer. Here softmax is important how it's applied. Softmax is applied row wise and hence each rows will be normalized between 0 and 1. So as I told you, several GCN filters can be stacked to learn the assignment matrix. I'm showing only one, but it's possible there are several GCN filters are there. And then on these filters, we actually, whatever output, we apply row-wise softmax. Because of the nature of row-wise softmax, each row is normalized to have summation 1. Okay, so if we look at the S matrix here, where we have 1 to n in rows and 1 to n out. Then if we look at the any rows, the sum over rows elements as I is equal to 1. Remember that each column here talks about super node or represents super node. Hence, if you look at the Sij element in our assignment matrix, it provides us a probability of assigning ith node to jth supernode. And based on that, we can actually go ahead and generate a coercion graph. Now with this information, the next step is to generate a graph structure using the assignment matrix. So we'll take input graph structure A in, we pre-multiply and post-multiply to get a coercion graph output A of dimension n out cross n out. So this is a simple operation. As transpose A in S will leads us to A. Our assignment matrix will ensure that we have clustered nodes into a set of supernodes appropriately. Now we have to find supernode features. To find supernode features, one way is linear combination of node features which are assigned to that particular this particular new A out. So F out So no features associated with supernodes in A out, linear combination S transpose F intermediate. This F intermediate is learned through GCN, and there are several GCN might be used to learn the F out. So typically F in is F in as transpose GCN filter right, A in and F in. Hence, the diff pool graph pooling operation can be defined as following or summarized as following, that we are interested in finding A out and F out, which goes through a set of diff pool operation where the in is F A in and F in. Next, we look at eigenpooling for generating hierarchical graph based pooling in supernode based approaches.